Hello all, thanks for tuning in. I'm Matthijs Gawehn, PhD student at the TU Delft with my supervisors Siert de Vries and Stefan Arnikov. And I'm going to talk about a fast depth inversion algorithm I've been working on, which is based on the dynamic mode decomposition. And I'm going to talk about how we are starting to apply this algorithm to different field sites in the world. So why are we doing what we're doing? This project started with let's map the underwater coast with drones. And we wanted as many people as possible to use the product we were going to make. So, for example, coastal managers, the life brigade, but also the industry. Now, what do these people want? They want something operational. So they want something cheap, easy to use, flexible, something that covers a large area and gives quick results. Now, then I come in and I think, why not use off-the-shelf drones? It would be great if you could analyze the live feed that is shown on these controllers and immediately return a result. That's not only a lot of fun, but it would also engage people, right? If it's fun, people will use it. Now, how are we going to do this? We are going to analyze waves and invert depths and surface currents from the wave properties, like algorithms as CBATHY, DISC, and XMFIT do, where you analyze a series of images, so frames from a video, for example, and you try to recover the wave numbers and wave frequencies, which you can then plug into the linear dispersion relationship, possibly with a Doppler shift, to get an estimate for the depth and the surface current U. Now, we want to analyze a live video feed, which means that we need to be fast. So our idea was to introduce dimensionality reduction techniques. Dimensionality reduction techniques usually take a bunch of data and transform these data into a lower dimensional form. So it's a simplification. And from there, you could transform the data back again. This is a principle you may know also, which is used a lot, for example, in image compression or video compression or anything. But what you can also do is you can try to process the data in this lower dimensional world and then get a product out of it. And why is this interesting? That's interesting because it's fast. In our case, the data is the video, and our processing technique is the dynamic mode decomposition. And the dynamic mode decomposition does not only get the video data into a lower dimension, but it also processes the data and spits out these dynamic modes, which are spatial structures that are bound to some sinusoidal time behavior. So they are coupled to intrinsic frequencies in the video. So here, for example, 0.15 Hertz, 0.19 Hertz, and 0.26 Hertz. How do we invert depths and surface currents from these modes? Well, you could also, if you want, you can read up on this also in a conference paper we wrote last year for the Coastal Sediments Conference. What you do is we have these modes with different frequencies, we grid them, and then you can do, for example, a two-dimensional Fourier transform to get your local wave numbers, but you can also do this with PIV, so with particle image velocimetry, that also works. And then you can stack up these layers and build up this pseudo three-dimensional spectrum, which you may recognize has some similarity to these spectra you get from three-dimensional Fourier transforms from other depth inversion algorithms, like, for example, XMFIT. And then finally, you do a nonlinear fit on the data. So you fit this dispersion shell and you get maps of depths and maps of surface currents. What is maybe also interesting is to dive into the possibilities for sampling. Dynamic modes show wave patterns per frequency that make up the video. Now, since we know the frequency per mode, we can predict what maximum wavelengths can be expected. So we may do better than just choose some regular grid cell size to determine the local wave numbers. So if we focus on this grid cell location over here, then for the highest mode, so for the mode with the highest frequency, we may choose a grid cell size that is this large. And then as we go to modes with lower frequencies, we can increase this cell size such that it fits the wavelength we expect. And these adaptive cell sizes, they lead to higher localization because you optimally use the wavelengths that are intrinsic to the frequency. You can do more. So while you may use all the pixels in the grid cell size of the dynamic mode with the highest frequency, you can use less pixels in modes that have lower frequencies. So we may start subsampling. And this subsampling will increase our computational speed. Now let's get to some results. So first of all, we tested this on Argus data from the field site of Duck in North Carolina. This is some data I got with courtesy of Kate Brody and Rob Holman. And what you see here is the result we get. So on the top left, you see the bathymetry estimate. In the middle, in the top middle, you see a difference map with the measured bathymetry, which, by the way, goes from about minus 1.5 meters to plus 1.5 meters in difference. And for that difference map, you may also look at the bottom right, where you see a direct comparison between the depth estimated on the vertical axis and the depth measured on the lower axis. Then on the top right, you see the surface current patterns we estimate. And on the bottom left, you see bulk values for the root mean square error and the bias as they evolve over time, so over iterations in this case. The algorithm works in iterations, and per iteration, it takes in 32 seconds of video, which takes about 6 to 15 seconds to process. And then the algorithm uses a Kalman filter to quickly converge these estimates. And what you see in this case is that after about 10 iterations, we are at a root mean square error that is lower than 50 centimeters. We also tested some data from Narrabeen in Australia. These are some drone data, some drone video that Killian Voss took for his master thesis. And the results we get there are as follows. You nicely see the bathymetry again, so the curvature that nicely follows the coastline. You see in the difference map, there is some larger error offshore. Well, I ascribe that to some wiggly bits in the rectification of the video. I know that this case is actually quite sensitive to what GCPs are used to rectify the image. So I will need to play a bit more with that. But regardless, you see in the RMSE that at the end of the iterations, the error has reduced to something lower than 120 centimeters, while it has started at more than 3 meters, which in this case nicely also shows the effect of the Kalman filter. And then lastly, we also analyzed some drone video from Scheveningen here in the Netherlands. This is a video that was taken by Jan Berg Arning for his master thesis. What is nice about this case is that the wave conditions were really calm. So looking at the images, I haven't looked at it exactly, but looking at the images, I expect the waves not to have been bigger than 0.5 meter. And what is nice to see is that the bathymetry is still estimated to quite an extent offshore without major errors. Well, you see them increasing at some point, but I'm really happy with these results. Here in this case, you also see that the RMSE is, after already a couple of iterations, lower than 70 centimeters. And what I like also in this case is that you see these current patterns evolving along the coast or running along the coast. And Jan Bert also checked currents with model results. And what I know from this case is that at least qualitatively, these current estimates should be correct. Well, this was the application of the algorithm. Well, finally, I'd love to apply this algorithm, of course, to more different sites. So if you have any cool drone movies, and it would be great also if you have a ground truth bathymetry for them, then I'd love to test those data too. So if your answer is yes, then please email me and we're taking on from there. Now, if you have any questions, I'm here.